Thanks for the introduction. And I'm going to talk about this work, which was jointly done with Srinivas and Anurag Salam and Gopal Dutt, who are both working at IBM in the US. So first of all, let me tell you why we care about Hamiltonians. So Hamiltonians are important because they govern some aspects of quantum systems. So say that the Hamiltonian H that is governing a quantum system, then what we mean by this is that it implies some properties of the system. In particular, when the system is at thermal equilibrium at inverse temperature beta, then the state of the system is going to be given by the Gibbs state determined by the Hamiltonian, which is just this state. So somehow understanding a Hamiltonian implies understanding a quantum system in the thermal equilibrium. Also, something important is that they not only determine the Gibbs states in thermal equilibrium, but they also determine the dynamics of the system. What do we mean by this? By this, we mean that the unitary time evolution operator of the system is given by this unitary, and this unitary is determined by the Hamiltonian. So if you let the system evolve for time t, what you are doing is applying this unitary. In other words, if the state at time 0 is rho, then after letting time t pass, then the state is going to be the conjugation of rho with respect to this unitary. So this is why we care about Hamiltonians. They determine very important aspects of physical systems. And what are we going to do with Hamiltonians in this talk? So we are going to try to understand some properties of Hamiltonians and try to learn them. What do we mean by this? So what you can imagine in this setup is that you have an unknown system that you can interact with, and you want to extract information of the system to get some information about the Hamiltonian. So something that you can wonder is if this Hamiltonian has a property or not. So this is a problem of testing a property of a Hamiltonian. So you want to extract information and decide whether the Hamiltonian satisfies the property or is far from satisfying the property. And you may also want to go beyond. You may also want to fully characterize the Hamiltonian, but that is very difficult. In general, it requires exponential complexity in the number of qubits, so that we don't usually want to do because it's inefficient, but maybe you can do that if you are promised some property of the Hamiltonian. So if you are promised some property of the Hamiltonian, you can use that structure in order to provide a better algorithm than a general one to learn n-qubit Hamiltonians. So the idea is that first you test, and if the Hamiltonian satisfies the property, then you use that also to learn the Hamiltonian efficiently. And which properties are we going to care about in this work? So they are two. They are locality and sparsity. They are very well studied properties, and they appear in nature in many cases. So now let me be more formal and state mathematically what is the problem that we are going to care about. So we are going to consider n-qubit Hamiltonians, which are matrices that are self-adjoint of dimension 2 to the n, and we are going to look at them through their Pauli expansion, meaning that we are going to consider Hamiltonians as linear combinations of Pauli operators. And here, the coefficients that appear in this linear combination are the Pauli coefficients. So usually, the property of locality is defined as a Hamiltonian is local if and only if it can be written as a sum of Hamiltonians that act non-trivially on at most a few places, meaning that they are identity, tensor, whatever Hamiltonian that only acts in a few places. But we can also define it alternatively in terms of the Pauli coefficients, and we can say that the Hamiltonian is K-local if and only if all the Pauli coefficients corresponding to Paulis that act non-trivially on more than K places are 0. So we can truncate this expansion to only local coefficients. We also say that the Hamiltonian is S-sparse if this linear combination only involves at most S non-zero Pauli coefficients. So these are the two properties that we are going to care about. And now what we are going to do is to define a distance in the space of Hamiltonians. We need the distance to define our problem because we need to, for example, for learning, define what is a notion of close Hamiltonian to each other. So a notion of a good approximation. And the distance that we are going to consider is the normalized Frobenius norm, which is given in this first formula, and is a norm that tells you somehow how the Hamiltonian behaves on average. And that is somehow the motivation to study the normalized Frobenius norm. And the reason why we care about the Pauli expansion is that the normalized Frobenius norm can be very well understood in terms of the Pauli coefficients. And that is thanks to this equality, which is known as partial identity, that tells you that the normalized Frobenius norm is just the L2 norm of the Pauli coefficients. So if we want to know something of a Hamiltonian with respect to the normalized Frobenius norm, we just have to extract information about the Pauli coefficients. So this is the distance. And now how are we going to extract the information? So we're going to extract information by a model that is suggested by the fact that Hamiltonians govern dynamics of quantum systems. And the model that we are going to use to access the information is to do several experiments of the following kind. We prepare a state of our choice, then we let time pass, which is the same as applying or querying the unitary time evolution, and then we measure. And we are going to do quite a few of these experiments, and then we're going to extract information of the system, and thus we're going to be able to answer questions about the Hamiltonian. So this is our access model, this is our notion of distance, these are the properties that we care about, so now we can be more formal when defining the problems of testing and learning. So the problem of testing is, given a Hamiltonian, try to decide if the Hamiltonian satisfies a property or is epsilon far from satisfying it. And the problem of learning is, given a Hamiltonian that you are promised that satisfies a given property, such as locality, try to output an approximation of the Hamiltonian. And these are very formal definitions, but we can also depict them here. And if we look at the left-hand side, we have a depiction of the problem of testing locality. And in this problem, you can imagine that you have two spaces, two set of Hamiltonians, the local Hamiltonians and the far from local. And what you're going to be given is a quantum system that it lies either in the inside or the outside area. And the task is to decide in which of the two areas the Hamiltonian lies. And on the other hand, if we look at the right here, what happens is that we have a depiction of the problem of learning local Hamiltonians. And in that problem, what we are going to be given is a red point inside the area of local Hamiltonians. And the goal is to try to extract information of the system in order to find an approximation, in order to find a blue point. So these are the problems that we are going to care about, and we want to solve them. But we not only want to solve them, we also want to do it efficiently. And to speak about efficiency, we need also a notion of figure of merit. So the two figures of merit that we're going to care about in this work are the number of queries, the number of times that we apply the unitary time evolution operator, and the total time that we need to evolve the system in order to solve the problem. This is the total evolution time, and this is just the sum of the times at which we query the unitary time evolution operator. So this is a setup, and now what we are going to do is to talk about what was done before this work. So there were a lot of works on learning, but first let me say that there are not too many results prior to his work on testing. So in particular, this kind of testing Hamiltonian properties was initiated by Bloom, Karanov, Kir, like not so long time ago, and they gave the first algorithm to test locality. And this algorithm ran in complexity. Here, when I mean complexity and when I state any kind of complexity is going to be an upper bound in the number of queries and the total evolution time. And they had a complexity of n to the k. And with that, they solved a question posed by several authors in a survey of Montanaro and De Wolf, and also in a paper by Adrian Se and Henry Yuen. They asked this question, so they solved it, and they somehow provide an efficient tester for locality. And they also provide a tester for sparsity that is query and time evolution efficient, but is inefficient in the classical post-processing time. This tester that they propose requires exponentially an exponential amount of post-processing time, so it's not fully efficient. So this is what was known before our work about testing, but there were many results about learning. So since 2019, there had been a lot of rigorous results caring about learning Hamiltonians by accessing them in a quantum way. And all these results, almost all, they only care about learning k-local Hamiltonians. And they also assume more things than just k-locality. They also assume that the Hamiltonian had some kind of extra structure, such as some kind of geometrical locality. By this, I mean that you can imagine that the qubits are in a grid, and then only the qubits that are neighboring in the grid interact with each other. So somehow the Paulis are more restricted than just to being local. So that was one of the restrictions of previous approaches. But other restriction was that they also assumed some kind of sparsity, and on top of that, they assumed that they knew which were the non-zero Pauli coefficients. So they didn't have to guess which were the Pauli coefficients. They didn't have to guess which was the support of the Pauli spectrum. In our work, we are not going to do that. We are going to do also like this extra step of first finding the Pauli support and then learning the big Pauli coefficients. And also something that happened in all previous works is that they had a dependence on n, on the number of particles. And this is somehow a summary of what was known before about learning local Hamiltonians. And there is no summary of what was known before about learning sparse Hamiltonians, because there was no prior result that really cared about learning sparse Hamiltonians. So this is the summary of previous work, and now I'm ready to state our results. So, okay, this may be difficult to parse, don't worry. We are going to go somehow one by one on these cells. And yeah, we have several results, testing and learning, and we are going to also make a difference between learning with memory and without memory. With memory, we mean that we have some auxiliary system that we can control, some extra n qubits. And in this table, we are going to assume that the error parameter is constant, just for simplicity. And also what we're going to assume for the rest of the talk is that the operator norm of the Hamiltonian is bounded. If you don't have such a boundness, you cannot solve these problems because you just have like infinitely many Hamiltonians, so you cannot discriminate them with finite resources, for example. But in the paper, we care about the dependence on this operator norm. This is a normalization that is also common in the literature. Okay, so first, let me focus on this cell. So in this cell, what we are seeing is that we have a constant tester for k locality. So that improves over the n to the k tester by Bloom-Karonov-Kirch. Then let me focus on learning and testing with memory. So before, we saw that the previous results had some dependence on n when testing and learning. And our results with memory do not have that. So that is nice. And we also have results without memory. We are not going to detail them, but let me say that we have some subroutines that allow us to translate our results with memory to results without memory just by paying at most a linear factor in the number of qubits. Also, these results are not time efficient, meaning that they require exponential classical post-processing time, but our results with memory are time efficient. So our results with memory just are efficient in every figure of merit that you can imagine. Also, something very nice is that for testing sparsity, we can do it without quantum memory, without using our subroutines, and still have an amount that is independent on the number of particles. And this is because we, instead of using our subroutines to translate results with memory to results without quantum memory, what we do is develop a new technique, which we will call Pauli-Hassen, and allow us to obtain this polynomial on S dependence for testing sparsity without memory. And this is also very interesting. I don't have time to talk about it, sadly, in this talk, but let me say that this also might be of independent interest, this technique, because this allows us to test for sparsity of Pauli channels, which is not the main topic of this work, with also polynomial number of queries to the channel. Okay, so the next thing that we are going to say is that our learners do not assume previous knowledge of the support. So we do not assume which are the coefficients, the Pauli coefficients that we have to guess, but we first find those that are not zero, and then we learn those. And finally, you may wonder, okay, you have gotten rid of the complexity on n, so you have shown that the upper bound for learning should not depend on n, but maybe it should also be independent on the other quantities that you have here, s and k. And that is not the case. We also saw polynomially weaker lower bounds that ensure that these problems need this dependence on S and K. So that is a summary of our results. And now what we are going to do is to talk a bit about some of these results. We are going to give a bit of detail about how we test with memory K-local Hamiltonians, and we are also going to talk a bit more about how we learn with memory both sparse and local Hamiltonians. First, let me talk about testing locality. So we are going to explain how we can prove this result, which says that one can test if a Hamiltonian is local or epsilon fall for local with only 1 epsilon to the 4 queries and 1 epsilon to the 3 total evolution time. And this is nice because, as we said, this improves the n to the k to 1 complexity that before was known by the work of Bloom-Karonov-Kirch. And this is not only nice because of that, but also the algorithm is super simple. So the way that is that simple that we can even depict it here. So we are going to repeat the same experiment many times, and then we're going to post-process it in a way that is not very costly. So let me explain this experiment. So in this experiment, what we're going to do is Pauli sampling. And what is that? So say that are the qubits of the system where the Hamiltonian H acts, and what we are going to do is to prepare an NPR pairs. We are going to take these qubits, we are going to duplicate every of them, and we are going to entangle them with an EPR pair with every of the new qubits. And we are going to assume that we have full control on this extra system, so that the Hamiltonian of the extra system is just going to be 0. Thus, when time evolution happens, what is going to happen is that you're going to make a query, you're going to apply the unitary time evolution of the system that you don't know times identity, tensor identity. And this is going to prepare the choice state of the unitary time evolution operator. So now, if we measure in the Bell basis, what we're going to do is to obtain samples from the Pauli distribution of the unitary time evolution operator. And this is nice because thanks to Schrodinger, no, not Schrodinger, thanks to Taylor expansion, what happens here is that if you take t to be small, then for every Pauli that is not identity, in this post-processing, we're only going to care about Paulis that are not identity, then in that case, we have that the Pauli coefficient of the unitary time evolution operator is proportional to t times the Pauli coefficient of the Hamiltonian. So somehow, this allows us to access the Pauli coefficient of the Hamiltonian, which is what we wanted to do to understand the Hamiltonian in the normalized Frobenius norm, thanks to partial identity. So this is what we're going to repeat a few times. We are going to perform Pauli sampling a few times, and then what we're going to do, the post-processing that we're going to do with these samples is the following. It's very simple. You're just going to count the number of times that you get a non-local term, and if you get many times a non-local term, then you're going to say that the Hamiltonian is not local. And otherwise, you're going to say that it's local. And this works because say that the Hamiltonian is not local, then you are going to have that many of these, you're going to have that somehow that the L2 norm of the non-local terms of the Pauli coefficients is going to be big, and thus, thanks to this equation, the non-local terms of the Pauli coefficients of the unitary time evolution operator is also going to be big. So that is why this algorithm works, and if you do the analysis, you get these complexities, and this is nice, but maybe this is too simple. Maybe you would expect that you can do something smarter, and indeed you can, and if you want to know how, I recommend you to go to the next talk in session A, which is by Daniel Liang and John Callaware, and they are going to show how to improve polynomially this complexity. So what they do is to take this algorithm to make it smarter, and what they are going to obtain is an 1 over epsilon to the 3 query algorithm that also uses just 1 over epsilon to the 2 total evolution. So if you like this talk, come with me later for session A. Okay, so now let me talk about learning Hamiltonians. And what we are going to do is first start with learning arbitrary Hamiltonians. So we are going to start with learning n-qubit Hamiltonians that are arbitrary. I told you that that cannot be done, and that was a small lie. So that cannot be done in the normalized Frobenius norm. In the normalized Frobenius norm, we know that it takes exponential queries. However, if you look at a coarser distance, if you look at a distance that is less precise, such as the L infinity norm of the Pauli coefficients, this can be done. And we saw that, we proved the first efficient algorithm to do this, and is the following result. So in this result, what we saw is that we can find approximations to every Pauli coefficients with thin error epsilon for arbitrary Hamiltonians using only these many queries and this much total evolution time, which is still independent on any other quantity. However, what we wanted to do is to learn in a distance that has at least some kind of physical interpretation, at least an average case distance, such as the normalized Frobenius norm. And that we're going to do by adding some structure, some promise structure to the Hamiltonian, and using this learning and structure Hamiltonian results as a subroutine. But before doing that, let me tell you that this Hamiltonian is also using Pauli sampling as a subroutine. So what this Hamiltonian does, what this algorithm does is first, it has 2 stages. In the first stage, what it's going to do is to learn the big Pauli coefficients. No, sorry, to detect the big Pauli coefficients. So in the first stage, we are going to do Pauli sampling, and you're going to store the outcomes. And if a Pauli coefficient is large, then what is going to happen, if the Pauli coefficient is bigger than epsilon, then with a few samples of this Pauli sampling process, you're going to detect that Pauli coefficient. So if you store them all, you ensure that all the Pauli coefficients that are big, larger than epsilon, are going to be sampled at this one. So you can set the rest to 0 and just focus on learning these few Pauli coefficients that are larger than epsilon. And to learn those, what we are going to do is to develop a new algorithm based on Clifford shadows that allows you to learn quite a few Pauli coefficients at the same time. And that is our algorithm for learning unstructured Hamiltonians. And the next thing that we're going to do is to explain how we can use this algorithm in order to learn Hamiltonians that are structured in a finer distance, such as the L2 norm of the Pauli coefficients of the normalized Frobenius norm. So first, let's talk about local Hamiltonians. So if you know that the Hamiltonian is k-local, you can use a tool from function analysis, which is the Bonnet-Bluzquin inequality. And Bonnet-Bluzquin inequality tells you that if you ignore all the Pauli coefficients that are smaller than a threshold, then you are going to still have a good approximation of your Hamiltonian if you learn the rest of the coefficients. And here, crucially, what Bonnet-Bluzquin inequality tells you is that this threshold does not depend on n. So using this result with an epsilon that does not depend on n, it depends on k and epsilon, and the real target epsilon, then you can get an algorithm to learn local Hamiltonians that does not depend on n. This is new, this is kind of surprising because like some people expected this to depend on n because at the end of the day you have n to the k possible non-zero Pauli coefficients, but not all of them are relevant, and that is thanks to the fact that you have bounded operator norm, and thanks to the fact that bounded operator norm can be paired with Bonnet-Bluzquin inequality to tell you that you only have to learn the Pauli coefficients that are larger than a threshold that only depends on k. Okay, so that is one thing that we do, and the other thing that we do is to assume that we have an sparse Hamiltonian, and in that case, our algorithm, what it does is using a rounding trick paired with this, and then you get this efficient query total time evolution learning in the normalized Frobenius norm for S-sparse Hamiltonians. Yes, and that's all I wanted to say. Thanks a lot.
Thanks. So it was nice talk. I just wanted to ask you about this Hamiltonian simulation. So if we transform the Hamiltonian to a form that is more easier to handle, does it suffice to look for that if it retains that k locality and s sparsity, is it is that equivalent form going to produce the same kind of evolution for that Hamiltonian?
I don't know which kind of transformation you.
For example, if you have a 2-qubit Hamiltonian, and if you go for Cartan decomposition, a KK decomposition, such that, for example, if you are transforming your matrix in such a way that you are going for a basis which have commuting terms.
Okay.
That may not conserve the sparsity of that Hamiltonian. So these kind of decompositions, do they give rise to the same kind of simulations which the original Hamiltonian was giving us?
Yeah, I'm not very familiar, so I don't know which transformation you are talking about, but I guess that if you preserve the property, maybe you can do better because maybe this transform Hamiltonian can have nicer properties and then the error analysis in the Taylor expansion is better or whatever. Yeah, I'm not very familiar. I can tell you that these transformations have been used for learning, but only for learning a single parameter. So there was a result that was telling you that how to learn a single parameter of a Hamiltonian very efficiently, and it was using these kind of transformations. But I think that there is no previous application of these transformations in testing or learning.
Okay, just last thing.
Yeah.
So for any given Hamiltonian that you have that you want to study the evolution from, so is it possible that we transform it in some another form of this Hamiltonian, and we can retain the same kind of simulation? Is it possible?
I don't know. Like
You don't know.
I'm not very familiar with simulation. Sorry.
Okay.
Hi. Thanks for the talk. I have a question about the motivation you mentioned at the beginning for testing and learning. So you said, oh, I can test, and then based on the outcome, I can use that to learn. Are your learning algorithms agnostic in that sense?
No, sadly no. Like if you, so well, the sparse yes, but somehow the local no. So if you have that your object is close to a K-local Hamiltonian, sadly, the Born-Blues-Green inequality that we use that allows us to have an independence on n breaks. So I think that is a very nice question. That is something that I wondered about. But also, do you know that the Born-Blues-Green inequality breaks? Because even if you take, like you can, if you have an arbitrary Hamiltonian that is unbounded in the degree, so it has unbounded locality, then the operator norm of the local part can be exponentially big. So then what you would get with Born-Blues-Green inequality would be a very bad dependence on n. It would be exponential. So yeah, it's at the breaks.
Thanks.
So my question was like when we are looking into the construction of the Hamiltonian, so sir, are you like using linear combination of unitaries or block encoding or any such methods? So I have seen that you mentioned polysampling. So is it used for decomposition of the Hamiltonian in your case?
No, we don't use any of those. Like
Okay,
we,
so
we use more like kind of Pauli analysis, which is somehow like the quantum version of the Fourier analysis in the Boolean cube. So that is our technique.
okay, and can this be scaled up to any different Hamiltonians like when you talk about transverse field Ising model? So is it possible to scale this up to any kind of Hamiltonian?
Well, I guess that is,
TFIM. So can we scale this up to any different Hamiltonian in other cases?
what do you mean by scale this? Like the other
Like, can
Hamiltonians?
we use the same learning methods for any different, if you want to implement this for any different Hamiltonian?
Well, like this
Yeah.
method for learning,
Yeah.
it works for Ising Hamiltonians because Ising Hamiltonians are too local. So
Okay.
our result tells you that for Ising Hamiltonians, you can learn them
Yeah.
with constant complexity because in that case, it's too local and the 2 is a constant. So
Yeah. And you're also testing any adaptive protocols for this structured Hamiltonian? Any future investigation in this?
yes. So like in fact, like we, for example, on Monday, we post a paper on Archive about testing learning Ising Hamiltonians.
This is a potential investigation in the future, right?
Well, in the past, like we have already done it.
Okay, in the
So
past.
I guess that you can extend that in some sense, but yeah, we have already looked at Ising Hamiltonians, for example.
Okay, yeah, thanks.
Yeah, just a quick question. Nice talk. You mentioned about like resources, like the number of queries or the time and so on. And I guess this is also the type of resources the other works look at. But kind of inherently, you're also having other resources like number of EPR pairs you form, number of qubits you need per run, and stuff like this. Do you guys kind of care about these resources, and do the other works care about them, and how does this stuff compare?
Yeah, like to be honest, I think that every work cares about the figures of merit that they do better. So it's a bit like difficult to compare results of Hamiltonian learning because, as you said, there is like many ways of trying to say how Hamiltonian learning algorithm is efficient. And yeah, we usually only talk about these two because like maybe these two are the most important, but also we keep track of the other resources. So of course you can also care about, as I was not mentioning it a lot, I was just saying that we were efficient in the classical post-processing time. That is also a very important figure of merit because at least at the end of the day, if you really want to run an algorithm, even when you have fault tolerance, you need to have efficiency in all figures of merit. So yeah, like we try to care and people try to care about these other figures of merit, but maybe they are not highlighted in every work.
Thank you for the nice talk. So for the testing algorithm in O1 queries, does it succeed with some bounded probability or does it succeed with certainty?
Yeah, thank you for asking that question. So I was hiding the dependence on the success probability, but it's just if you want to success with probability 1 minus delta, the success probability is just log 1 over delta.
Hi, hello. Thank you for the nice talk. And like you had a table with the results, a summary, and then like you could compare the memory price, and then like that's the one. And then for A as sparse, and when you want to learn it without memory, you pay a linear price, but for the K local, you pay just a logarithmic price. So like could you comment high level, because there's quite a lot of difference in the prices that you pay, and I don't know how you find it. And if
Yeah.
it would be possible to just lower, or if you think that it's possible to lower the linear price and just pay a logarithmic.
Yeah, I don't think so, because somehow like the way that we do that, we use this subroutine and then we use this subroutine for all Pauli coefficients, and somehow when you have a sparsity, you only know don't know anything. So you have 4 to the n Pauli coefficients that you have to consider, and by a union bound, this turns into a log 4 to the n complexity overhead. So log of 4 to the n is just n. So that is why in this case you get the n. But on the other hand, when you know that the Hamiltonian that you want to learn is k local, you only have to look at n to the power k coefficients.
If it is as sparse, can you just consider less than 4 to the power of n?
No, because you don't know which are those, like it's as sparse, but you don't know which are the s Pauli coefficients that are not 0. So you don't assume that.
Okay.
If you assume that, of course, you would be able to do it with, instead of log 4 to the n, you would be able to do it with log s. Yeah, but in this work, we don't assume that to be information of the about the Hamiltonian.